Hello everyone. Hello everyone. In this presentation, I would like to talk about SLisp2. Uh, and SLisp2 is simple because it's not very sophisticated, but self-hosting Lisp compiler for x86-64. So generating machine code for 64-bit processor, PC processor. And first of all, who am I? My name is Andrea Garfini, and I started programming in 1981 on Apple II computer. And I worked as programming in many fields. I still love programming after more than 40 years. And I mostly use C++, both at work and for my personal projects. But I have a passion for programming languages and compilers, interpreters, how things are implemented, stuff like that. And a few years ago, I spent some time investigating on Lisp and literally fell in love with the language. So a couple of years ago, I realized that this Lisp2, simple Lisp2 system. And number two is because there was a version 1 before, and actually there is even a version 3 that I'm not working on in my free time. So, general overview. It's a simple Lisp implementation, does not try to get to Common Lisp. It's quite different from Common Lisp. And the lists are implemented as array. So there is no car, CDR, stuff like that. And I know this can be shocking for if you are a Lisp programmer or if you ever investigated on Lisp system, because this seems to be kind of a prerequisite, a must for a Lisp system. In my opinion, const pairs for implementing Lisp are a bad idea. They were okay in 1958 for the McCarthy paper, but they were not a good idea, and because for many reasons. And I think arrays work better for Lisp, for lists, and you can implement a Lisp system without having to write car or CDR or something like that. And there is a garbage collector that is a simple one that just stops the words and uses a mouse sweep technique. And as I said before, implements the x86-64 machine code generation, the compiler. And more specifically, I'm using the System 5 ABI. And this means that it works on basically any 64-bit operating system on this kind of processors, so not ARM processors, except Windows, because Windows uses a different ABI for reasons. And one important point is that there are no dependencies. So I'm not using an LVM, I'm not using any kind of stuff. Otherwise, I would have much many more targets, but I'm just directly generating the machine code. And I'm not saying this is a good idea, but this is what I did. Okay. Data types. I use a 64-bit for each value, a slot that contains a value 64-bit wide. I'm using lower bit for tagging. I'm not using non-tagging. That's a very common technique. And the reason is that using the high bits is very annoying from assembly. And because the CPU does not, the access to those bits is annoying because you have to shift a lot of times. So maybe it's actually optimized, so this code is really free. But the assembly is much, the assembler code that you need to write is much uglier, so I prefer to use low bits. And I have a floating point tables and the fixed numbers. Floating point doubles are almost doubles. That's why there is a little tilde in the slide, because the lowest bit is used for tagging. So if the lowest bit is 0, then it's a floating point number. If it's 1, then it's something else. And I'm using another 3 bits for the tagging. So I'm using the 4 lowest bit for tagging, basically. And but this, in my opinion, is still a better idea than using the higher bit because of the way the processor manipulates 64-bit data. And there are strings, symbols, of course. There is a short string and symbol optimization. Actually, I checked a few moments ago the code. I was not remember correctly. The last time I worked on this was about 2 years ago. And I was remember that the symbols are actually just the indexes in a symbol table. So, but there is an optimization for short strings. So strings up to 6 characters do not require any allocation. And there is also gensim optimization. So when I needed to generate a symbol for macro, the interning is just no allocation is required, not even in the symbol table. And then I have objects. I will explain later what the objects are, and but I use it for many different things. I have a special case for cells. Cells are very tiny objects that just contain one value, and they're used for closed over variables in closures. And then I have machine code objects. And those will be explained in much better detail later. And another thing that I have is that I support errors. And error can actually be any kind of other value, excluding floating point numbers, but any other kind can be an error. And being an error means that if you return an error from a function call, the result is an error, the current function quits immediately. So it's basically kind of an exception, but I'm not implementing. There is an ABI for exception in System 5, but it's horribly complex. So I didn't want to get into that mess. In my opinion, given the implementation is so complex for cross-language exceptions, probably exceptions are a bad idea. I still need exception, but I want to also implement the conditional system. Maybe I will do one day when I find time. That's maybe never. And but those auto values are basically hot in the sense that who gets them in the hand must return immediately. There is only one case in which this does not happen, and it's with a very specific instruction, that is the try instruction, that can handle the error and unwrap getting the error content and do some managing. So it's basically exception, but not implemented using the System 5 ABI for exception. And then I have objects, as I told before. An object is a tag that is normally a symbol, but can be actually any value. There are 0 or more slots, generic values, and those slots are seen by the garbage collector. So if an object is alive, then all its slots, all the object pointed by its slots are also alive. And then can have 0 more row bytes. So you can have an object that is, for example, an image that is just made up of the pixels, and there is no extra memory consumption because the pixels are just taking the minimum number of bytes that are required for them. And one important thing is that you can, for a given object, if you don't change the total size, that is the tag plus some bookkeeping plus the slots plus the row bytes, you can trade in bytes and get in more slots, or trade in a slot and get in more bytes. This is done using a resize operation. because this does not require a location, because the object can stay in the same position. So all the reference to the object remain valid. And this is basically like, let's say, C++ std vector. You can be used also like a C++ std vector. And it's also how it's kind of used when I'm manipulating list. And objects are used for list, for closures, for a lot of internal objects too, for the compiler and stuff like that. And then I have a machine code object that is not a real object. For technical reason, I don't remember, but there was a reason for this. And they are still garbage collected, so they have slots and bytes, but they also have a function pointer. And that was annoying to put in bytes. I don't remember why. But anyway, so what you see on the slide is basically the definition of the structure. So there is a next, this is used by the garbage collector. There is a function pointer that is EP that contains a pointer to a function accepting a value pointer and an integer. This is a pointer to the first argument and how many arguments I'm passing in. So this is basically the calling interface for callable objects, and the return value is a value that I must return to the caller that can be hot. So maybe this is kind of an exception. And there is no support, and it's not easy to add support for multiple return values with this interface. Except maybe adding an extra parameter in the beginning, say, or having something that says that the first slots are actually a return value, something like that. I didn't have to think. I never implemented actually multiple return values. I did never actually use I think never actually used multiple return values in common list. But so this is the interface. One important thing is that it's compatible with the C ABI. And so this works, I can use a machine code object for pointing to a function I implemented myself by hand or in C++, or a function compiled by the compiler, or even an interpreted function, where in this case it will be pointed to a library function that is basically calling eval. And in the slots, I will have a pointer to the source code for the function to call the interpreter on. Then I have a number of slots, a number of bytes, like a regular object. And then I have this x of 1. I'm forced to use a 1 because I'm using C++, so I cannot use an empty array at the end of a structure. This is not supported for, I don't know why. So there is this number of slots and number of bytes. The slots are normally used for the constant used in the compile code. And also and also for the pointer to the source code in case of compile code, because when you get an error, you also get the source code where the error happened. And bytes instead contains the actual machine code in case of a compiled function. And there is one extra detail, that is the callable may be a closure. And in case of a closure, just a pointer to a function with that signature is not enough. And so what I'm doing is compiling a trampoline. So basically, you're calling a regular function. This function gets the extra data needed, that is the third parameter, the third value pointer parameter. That is basically where the captured variables are. So where the slots are for those variables, the context for the closure, basically, the internal state for the closure. And but since this is done using a trampoline, is the code needed for calling a function is is the same, no matter if it's an interpreted function, a library function, or a compiled function, or a closure. And so this is an example from the kernel. This is the call utility function that basically calls a code object passing certain arguments in args and na. We can see that the assembly for this, for the system file ABI, would be that in RDI and RSY, you will get a pointer to the first argument and the number of arguments. And the RDX, only in case of closure, would be the pointer to where the cells, the captured cells for the context, closure context are. The return value is RAX. As you see, it's just a function call, basically translated directly to a function call. And those three registers are the reason for which this is not compatible with Windows, because Windows, for reason I don't know, I don't understand, except maybe comes from an era when Windows was actively trying to be incompatible. But there is a different calling convention, so it's not using those registers. So the compiled code from this compiler would not be valid the code, and this would just crash. Okay, so how is the system implemented? There are 4 main files. The first file is SLisp2.c++, CPP. Is about 2,000 lines of code, less than 2,000 lines of code, and implements the low-level kernel that is implemented in C++, but it's actually just a C with, I don't remember which feature I'm using for C++. I can probably convert all of this to C because I'm not using anything fancy. There is no template and no standard library. There is nothing at all. So maybe I will migrate this to C. But now it's C++. And also implements the base values, the numbers, strings, stuff like that. Generic objects, so you can allocate object, the allocate object. There is a garbage collection. There are all the base library functions. So the basic function you need to, I don't know, substrings, something like that, to start with the system. And those are implemented in C++. We will see some code for them. And there is also, this is very important, a base interpreter. What does it mean, base? This Lisp system is basically created using 2 Lisp. The first Lisp is very, very minimal, and just defines a few special forms. That is quote, there is a sequence. I call the sequence a sec instead of program, like it's called in Common Lisp. Then set Q for setting a variable. Then you have a condition, you have while. I got a while loop instead of using a generic do. And I have a function creation that is a func. I didn't use the name lambda. And a few others, including, for example, try, something like that. But this is very, very minimal, just minimal implementation of for the Lisp system. And then there is, in addition to a few special forms, there is a function application, so function call, and macro expansion. And there is also a special reader that is actually able to read an S expression from a binary format. And this binary format is a simplified format, so the reader is a special reader that reads this binary format where all the data is already made as easy as possible for the reader to load. For example, for list, you have just the number of elements and then all the elements following, or numbers are just stored directly and stuff like that. And so that's it. This is the kernel, basically. Then there is boot0.lisp. That is a file written in Lisp, about 1,000 lines of code, that basically elevates the level from this minimalistic Lisp to a full language, a full usable language. And so, for example, define list, define map, define first, slice, let, set f, and stuff like that. Also implements quasi-quoting. This is very important for being able to use macro more easily, to create macros more easily. And there is also a full reader with also support for reader macros. And there is a REPL that is implemented based on the reader, on eval, and the ability to read from the standard input directly. That is a library function for the function. So the REPL is actually implemented in Lisp itself, and the reader is actually implemented in Lisp itself. And then we have this bootreader.js that is just 100 line of codes. That is a simplified reader for boot0.lisp. So to load this file, I'm using this boot reader that is very simplified, does not support references for back references, does not support floating point numbers even, does not support reader macros, of course, and output a binary format. It's basically a program that just reads this Lisp source code and generates a binary boot0.bin for SLisp2 to read. And then we have the compiler, the real compiler, that is about 1,000 lines of code. And this is basically implemented using two functions. The first one is compile, that accepts a function form. So that's the minimum input, the source code of a function form, and the current compiling environment. That is normally null when you call directly, but can be the compiling environment from the outer context when compiling a closure, and so it's recursive, and this M variable will be populated by compile itself. So when you call it directly, you always pass null. And the output of the compile is bytecode. So it's still a logical representation of the code expressed in terms of sort of a virtual machine. But there is no interpreter for the virtual machine. It's just a representation for the code. And then there is another function that is x86-64 that actually takes a bytecode object, that is just a list of bytecode operations, and generates a code object that is actually machine code that you can call. So a callable object. And the output of this bytecode is always a function. Maybe when you call it as a result, you can get a closure, but the output is never a closure because when you get the bytecode from compile, you have been passing a null environment. So these are always regular functions, not closures. And another thing that a compiler Lisp does, as the last lines, is replacing eval with a function call of x86-64 of compile of a function with no arguments and the expression you passed in. So basically, is replacing an evaluation, the interpreter evaluation, to a call of a compiled function. And so after you load the compiler.lisp, everything you type in the REPL is actually compiled to machine code directly. Of course, all existing functions are still calling the interpreter, but new function you define, as those are evaluated by eval, are actually compiled to native code. So how the bootstrap works? Well, first of all, I omitted this from the slide because this is done only once. Is you create a boot0.bin by running the utility for doing the original parsing. Then you load the compiler.lisp, and this loads the compiler in that is being interpreted at this point, and also replaces eval, however. So this interpreted compiler from now on will be compiled to machine code everything you type in the rep. Then you reload, because this was already loaded when you started the system. You reload about 0.lisp. And so all the utility functions that basically rise to the level of the language are replaced with the native code, including your macros. So this boot 0.lisp basically replaces all the interpreted function, all the interpreted Lisp function of the system to be native code. And then you can reload the compiler a second time, because this time the compiler, the interpreted compiler is compiling the compiler to native code. So after you completed those 2 steps, the interpreter is not used anymore. The minimalistic interpreter written in C++ is not used, because all the code is machine code that has been either written because it's a base library function written by me by hand, or is a machine code that has been generated by the compiler itself. And so now there are a few bad things I have to say about this system. The first is code quality. You can see here a very simple function, an identity function. I use this syntax that is closer to scheme that more than common Lisp, but is basically in defining a function named ID that takes a parameter x and just returns the parameter. And this is the machine code that is generated. And so, yeah, it sucks a lot. However, I must actually say that there is the code for this function cannot be just a couple of instructions. And one reason is that still there are checks. For example, if you call ID passing no parameter, passing 2 parameters, you get a runtime error. So some kind of checking and error returning code must be generated. But this code in the beginning part specifically is also doing something that is pointless for this function specifically, because it's creating a safe zone for the working area for this function. It is a safe zone in case a garbage collection is triggered, because any object allocation can trigger a garbage collection. And so all the internal state of the function that are actually active on the stack needs to be preserved, because those objects in the temporary of those functions maybe are not reachable from the roots, but the garbage collection might not touch them. And so this means that I cannot just use the stack normally. I need to inform the garbage collector what I'm doing. The garbage collector is an exact garbage collector. It's not just using, it's just not doing a blind search. So actually starts from the roots and only follow the links. It's not looking for just bit patterns. And so the first instruction, push RBP, is saving the current value of working stack state. Let's go this way. Then I'm basically linking in a new safe slot. This function will just need one temporary slot for computing the value. And that's because the code generator is bad, because actually there would be no need for any temporary, but it's just a temporary, but created this slot and then set this slot to 0 to avoid the garbage collection to see uninitialized memory. And then at address 21, you can see that it's checking that the number of arguments is actually 1. If the number of arguments is 1, then it's jumping to 36, so everything is okay. And here there are 3 instructions. The first one is loading the first parameter in array X, and then is storing this parameter in the temporary location. And the third instruction is loading array X from the temporary location. This is why this code is terrible, because there is no kind of no real optimization of any kind. And after this is done, basically the safe location is removed from the linked list. Popping RBP means that we get back to where the value was, and we can actually return. In case of an error, I'm loading at others 27. What you can see, this is just a symbol, an error for a symbol that's bad arguments, basically. It's basically say bad arguments, and it's jumping to 48, that is the quit default function. So if you're not passing exactly one argument to this code, you will get an error. So the code generation sucks. In this case, a little bit was still necessary, was just not, but the 3 instructions instead of 1 is kind of annoying, because to implement this by a decent logic, you will just need to load the first argument into array X, and you are done. Of course, you must check, like I said 1 second ago, that you actually got passed one parameter, exactly one parameter. Otherwise, there is a runtime error. There is no actually, see, commonly expressed several options to decide between safety and performance. I don't have any like that. There is anything like that. It's just generating always the same code. Okay, this is a little part of the bytecode to native code translator, where you can see how to basically how I am creating the machine code. And this is basically by emitting, you see, emit 0x55. This is the machine instruction for push RBP. So I basically wrote all the statement I needed in assembly, assembled them, and checked out what were the hexadecimal values, so I could create the code. And this is, for example, the enter bytecode instruction. The next one is actually unjump if not equal to a floating point constant. So there are a few kind of specialized operators for those cases. But this is done, like I said, by emitting directly exactly the bytes for the native code, x86, 64. Okay, this is an example of bytecode compiler. So I loaded the compiler, and the return value from compile is just a list. So I'm basically looping over the result of compiling. As you see, I'm compiling a function that multiplies an argument by itself. I'm passing the null context for the compiler. This is and I'm printing the output. So the first bytecode instruction is cells, that says there are no cells, basically cells without any information, and this means that this function is a pure function, is not a closure. There is no context that has been captured. And enter 3 means that this code will need 3 temporary slots for doing the computation. Argcheck is checking that there is exactly 1 argument. And in case of an error, just jump into G6. As you see, G6 is the exit point where there is the statement, the instruction leave 3. And then I'm loading in slot 0, temporary 0. I load in the function multiplier, the function multiplication, and is a global. Now you see there is load 0, that is the target slot. f/star is the name of the function, the star function, multiplication function. It's a global with index 0. So is the first global Global index 0 means global to this function. This is the first global for this function. And then you have load to slot 1, the first parameter, that is local 0. And load again the same in slot 2, in temporary 2. I'm loading still the same parameter again. Then I'm calling the function. And as you see, call 0 means the call starts, the function object will be in slot 0, and the parameter will be the following slots. In total, there are 3 elements. So I'm basically calling a function passing 2 arguments. In case of an error, this means if I get an odd value, I'm jumping to G6. This is also something I could actually optimize by telling which functions are allowed to return odd values, which are not, so to save some checking. The checking is actually pretty fast, because it just requires 1 bit check after the function call. And but this is something that could be added to save some code, to simplify the code generation. And then at the end, I'm storing the result. And it means I'm storing this is basically means load the first temporary. The result will always be in the first temporary slot into array X. This is the meaning of store result. And so that's it. So let me show you a little bit of code too. And this is as SLisp2.cpp that, like I said, I'm using 4 bit for tagging. Actually, the lowest bit tells me if it's a number or not, is a floating point number or not. Then the other bits I use the for fixed num, symbols, short strings, long strings, general objects, cells. The cell, like I said, are for captured variables, and code object and error. If the lowest 4 bit are all set to 1, this means that this value is an error, but actually the is just a flag for all the other bits that we shifted by 8 bits. So I can shift back 8 bits and the value is still usable. This because all those pointers are never able to use the upper 8-bit for other reasons. The other is not 64-bit is actually I think 64, 56, 48-bit really not is not fully 64-bit. There is, as far as no processor actually uses 64-bit in full right now. And so this is tag mask. There is all the tags, stuff like that, and memory locations, and so on and so forth. So let me check for eval 1, maybe eval 1. Let's see. Oh, eval I1. This is the interpreter. This is the interpreter, and like I said, there is a lot of stuff at the beginning. Then I'm checking, is this the quote form? Is this the sequence form? Is this a set Q form? Is this a while form? So it's a very, very simple stuff. And and the NOR, I don't remember why I implemented an NOR instead of just, anyway, there is a cond function that this is creates the basically a code wrapper for that will point to a function, a code that actually calls the interpreter itself. So it's basically wrapping the source code and capture the local environment. And this is try, and this is the basically the function application or macro expansions, and that's it. This is the call. And this is everything. So this is the minimal interpreter that I implemented only as those five. This is boot0.lisp, and as I said, implements very primitive functions like map, map star, filter, first, second, and so on and so forth. As you see, I'm defining to define a macro. This is different from common Lisp because I'm using just a single namespace. But while looking up the first symbol of a form, I'm prefixing with them to see if there is a macro with the name, and then with F to look up for a function. So there is really technically there is just one space, but the way the interpreter works is like if there were three namespaces, one for the macros, one for the functions, and one for the values. And here I'm defining the macro. That is basically you see a function of the given a list returns list rf as 0. So returns the first element, basically, because list, as I said before, are arrays for me. So there is an ref operator to access the element. And then I'm defining the function first. So this was the macro first. And defining the function first, that is actually calling the macro first. This, I admit, looks weird, but this allows me to have both the code that is actually expanded. So call to first is actually just a rolled ref as 0, but I can also use the first with map. So it's also a function. So it's a macro and is a function. This is something that is not possible in Common Lisp. Not clear to me why that was the decision, but this because that would be nice even in Common Lisp, in my opinion. Then I'm presenting, for example, if, because the only thing I have is cond. Append is when, unless, not, let, slice, all the stuff. I'm defining def macro, and I am defining def. This is kind of because until now I was setting directly the namespace. After this point, I can use def macro. After defining def macro as a macro, I can use def macro. And after defining def, I can use def. And so that's it. That's a boot 0. Like I said, it's about 1,000 lines, and implements also a few random things that I think are not used, like maps and something like that. Okay, and binary serialization. Okay, this is the REPL. This is the implementation of the REPL that is written in Lisp. There are a lot of tries, because maybe the parsing phase, maybe the execution phase, stuff like that. And this is bootreader.js that basically transforms this text into a binary blob. Boot bin, it's not boot0.bin. We have to correct the slide. And so this is the code, is a 100 lines of code. And finally, there's the compiler. This is, I think, this is the most interesting part, where there is this x64 bytecode code generator that are setting input a bytecode. And this is the calling convention. Like I said, FBI, RSI, RDX. And code objects are always relocatable, and because every memory address is relative to IP. And closure implemented using trampoline, like I said before. And so this is a few utility function, and then the code that I shown. So for each code, I hand coded the assembly that I wanted for that code. There is really no optimization, no serious reasoning. And after this, there are a few macros for is the definition of the compiler. This is the compile function. The compiles that, as I said, requires a function form and just returns a list of bytecodes. So, as last, just a few example, I want to show you the thing in action. So this is I'm starting the SLisp2 system. So what happened is basically that Lisp0 was loaded, and this is the REPL that is interpreted by the interpreter. So for example, can put 1 plus 2, or we can define fibo x if less than x2 1 plus 0 minus x1 0 minus x2. Okay, I got my function. If I say fibo verb, I get the result. If I do time fibo turbi, you see that takes quite a lot. That is 500 milliseconds. And it's important to know that made 2.7, almost 2.7 million allocation calls for a total of 130 megabytes, something like that. And the GC, the garbage collection, has been called a little less than 300 times, 270 times. And so this is the interpreter. So the compiler has not been used at all. Now, if I load compiler.lisp, now I have the compiler that has been loaded and is an interpreted function. So when I'm compiling stuff, is the interpreter doing executing the compiler that you just saw before and generating machine code. But the result will be machine code, even right now. So whatever I type now, so if I 1 plus 2, now this has been compiled to machine code and executed, and then the machine code becomes collectible by the garbage collector. And if I do this timing, I get the same value as before. So 640 milliseconds this time for random reasons. It's very difficult to get consistent time with modern processor, because they keep switching frequencies and stuff like that. And so this was the same as before. However, if I now define the function, this definition has been now compiled to machine code. So if now I execute the code, you see the execution time is now 26 milliseconds, so 30 times faster. And there was no allocation call at all, because the compiler is able to see that there is no reason for capturing anything in this function. And so there is no memory, no extra memory. A stack is sufficient to implement this function. And so there were no allocation, no CC, nothing. And so we got a code that was 30 times faster. But like I said, the compiler is still interpreted. Now, if I load boot0.lisp, I'm reloading the base system, basically, the full system. But this time, all this code has been compiled to machine code by the interpreted compiler. But now I can reload the compiler, and now the boot is complete. So now the interpreter is not used anymore. I didn't add, maybe I will add a counter for how many times the interpreter has been called, but I remember checking. The interpreter is not called anymore from this point on. So this time, if I do this function definition, the compilation has been done by machine code. The result is machine code, and of course the execution time would be the same. Noise permitting. And that's it. So we completed the bootstrap. Something that is not yet present is the ability to save the code to disk. This is part of the implementing the boot0 .lisp, but has not been used to save code object to disk and load the code object from disk. If that implementing that, I could probably create a standalone executable by maybe concatenating the SLisp2.exe with other code objects with the compiled code object I want for the entry point for the program, something like that. But basically, this compiler made the bootstrap. So this completes the video. It's about 50 minutes, way longer I was expecting. I hope it was interesting, and see you next time.